Hello everyone. Today, we will introduce the fourth part of the printing process course. Test printing process. Project 1, Pressure Adjustment. As we all know, printing pressure is a crucial control element in printing. Proper control of printing pressure is fundamental to successful printing. This section mainly covers the following aspects. First, basics of printing pressure, including its source, representation methods, and printing pressure distribution. Second, printing packing. Third, calculation methods for printing pressure. Fourth, methods for adjusting printing pressure. First, what is printing pressure? Printing pressure refers to the interactive force between impression bodies when ink is transferred from the printing plate to the substrate during the printing process, as shown in the diagram below. When the plate cylinder and blanket cylinder come into contact, deformation occurs, generating interactive pressure, which we call printing pressure. In printing, the pressure primarily comes from the packing materials. First, let's look at the plate pressure between the plate cylinder and blanket cylinder. The plate cylinder has minimal deformation and can be approximated as a rigid cylinder. To adjust the pressure, packing materials are usually added beneath the printing plate. Second, the pressure between the blanket cylinder and impression cylinder, known as impression pressure, comes from the packing materials on the blanket cylinder, including the blanket and its underlying packing. Generally, this deformation is relatively larger in offset printing. Printing pressure must exist and serves the following purposes. First, compensates for microscopic unevenness on the surfaces of the opposing cylinders, ensuring uniform pressure distribution in the impression area. Second, ensures full contact between the opposing cylinders, allowing intermolecular forces to facilitate the transfer of the ink layer. Let's take a look at the schematic diagrams above, which illustrate the printing pressure between different cylinders. The representation of printing pressure is mainly divided into two types: direct and indirect. Direct representation can use parameters such as total pressure, line pressure, and surface pressure, which is an accurate method. However, it is difficult to directly measure the specific pressure value during printing. Therefore, in specific operational processes, direct representation methods are generally not used to indicate pressure. Therefore, during the printing process, we typically use indirect representation methods. There are two types of indirect representation methods. The first is to represent printing pressure through the amount of compression. The second is to represent printing pressure through the width of the impression line. Let's take a closer look at the pressure between the two cylinders. The pressure distribution between the cylinders is uneven. Within the impression arc, the pressure varies along the circumferential direction. The pressure is greatest at the center line and decreases sequentially on both sides. Along the axial direction, the pressure in the middle is lower, while the pressure at both ends is higher. Second, printing packing. We know that the existence of pressure is mainly due to the role of packing. Common packings used in offset printing include paper, plastic, woolen cloth, old blanket, etc. The packing used in printing is often a combination of different packing materials. Offset printing pressure is commonly expressed indirectly. For printing packings, according to their elasticity, they can be divided into hard, neutral, and soft. Hard packings have greater elasticity, neutral packings have moderate elasticity, and soft packings have lower elasticity. Hard packing is composed of backing paper and a blanket. That is, placing several sheets of paper under the blanket to form hard packing. The cylinder indentation width is 426 mm, with a compression amount of 0.04 to 0.08 mm. Such packing is relatively rigid, with a high elastic modulus, meaning that small changes can generate significant printing pressure. Moreover, most offset presses use contacting cylinders, which makes the cylinder operation relatively stable. Some domestic web offset presses and most imported printing equipment use hard packing. Neutral packing is composed of thick paper, cloth interlayer, and rubber blankets. For neutral packing, the impression line width is 8 to 10 millimeters, with a compression of 0.1 to 0.2 millimeters. The printing performance of neutral packing is between that of hard and soft packings, with a moderate elastic modulus, good dot reproducibility, and relatively low plate wear. At the same time, neutral packing is divided into neutral slightly hard and neutral slightly soft types. Soft packing generally consists of thick padding, woolen cloth, rubber blankets, etc. For soft packing, the impression line width is 10 to 12 millimeters, with a compression of 0.2 to 0.4 millimeters. It has a lower elastic modulus, meaning that a relatively larger amount of compression is required to generate the same printing pressure. Some domestic offset printing equipment uses soft packing. Different packings have distinct characteristics. First, their sensitivity to printing pressure varies. For the same minor pressure change, hard packing is more sensitive to pressure fluctuations than soft packing. Therefore, hard packing imposes higher requirements on material flatness, press precision, etc. Otherwise, uneven printing pressure may cause streaking. Take a look at this curve graph. The horizontal axis represents the compression amount. Observe the two curves for hard and soft packings. At the same compression amount, soft packing generates less pressure, while hard packing generates more pressure. Therefore, printing equipment using hard packing requires higher precision. Second, the size of the transfer area differs. Generally, hard packing has greater pressure, but a narrower impression area, while soft packing has lower pressure but a wider impression area. The wider the impression area, the larger the range of image dot extrusion and deformation, and the poorer the sharpness around the dots. Conversely, smaller deformation results in higher sharpness. So hard packing offers better image dot reproducibility than soft packing. Let's look at this schematic diagram. Third, different pressures led to different degrees of elastic decay of the blanket. After repeatedly bearing the cylinder pressure, the blanket gradually fails to return to its original thickness, called elastic decay. Therefore, printing pressure decreases due to this phenomenon. Soft packing generally experiences a 20 to 30% pressure drop, neutral packing about 10 to 15%, and hard packing approximately 5 to 10%. Next, let's look at the measurement of printing pressure. The measurement of printing pressure can be indirectly indicated by measuring the packing materials. We can use relatively precise tools, such as a micrometer, to measure the thickness of the packing materials, mainly the blanket and its padding, or the thickness of the printing plate and its underlying padding. After measurement, the gap between the cylinders is calculated to obtain the amount of compression, thereby indirectly indicating the printing pressure. The above is a schematic diagram of the measuring tools. The advantage of measuring pressure through packing materials is convenience, but the disadvantage is lack of precision. First, the blanket and its padding materials are not rigid bodies, often with deviations. Second, after the blanket is installed on the cylinder, errors caused by different tightness levels are relatively large. To reduce errors, the blanket can be measured with metal sheets clamped around it. Additionally, measurements should be taken as averages to minimize errors. The second method for measuring pressure is the padding gauge method. The measuring tool is a padding gauge, commonly known as a cylinder diameter gauge, which mainly measures through the pillow excess or pillow clearance. Pillow excess refers to the difference between the cylinder side and the pillow, with positive values for those above the pillow and negative values for those below. We can use the cylinder diameter gauge to measure directly on the machine. the pillow surface is finely machined, resulting in more accurate measurements. The above is a schematic diagram of measurement using a cylinder diameter gauge. For different printing equipment, the arrangement of the cylinders in the printing unit varies slightly. The left diagram shows a shoulder-type pillow, while the right diagram shows a non-shoulder type pillow. For the left printing equipment, the clearance between the pillows is 0, and this structure is mainly used in modern high-speed offset presses. The right structure is used less and less, because the clearance between the shoulders causes equipment vibration and poor printing accuracy during high-speed printing. The third measurement method is called the indentation width method. During the transfer process of an offset press, a specific amount of compression deformation corresponds to the indentation width between the cylinders. Therefore, measuring this indentation width can indirectly indicate the printing pressure. Therefore, we can complete the measurement by first creating an indentation, then measuring, and then calculating. The measurement of the indentation width method is shown in the figure below. After measuring the pressure, we can precisely adjust the printing pressure. The first method is to adjust the thickness of the packing. This mainly involves adjusting the packing material of the printing plate. Of course, adjusting the packing of the printing plate not only affects the printing pressure, but also relates to the pressure of the inking rollers and dampening rollers, the circumferential length and synchronization of the printed image, and roller pressure. Adjusting the blanket cylinder packing can simultaneously increase or decrease the plate pressure and impression pressure. So comprehensive consideration is needed during the adjustment process. The second adjustment method is to adjust the center distance between the cylinders. From the perspective of gear rotation, the gears are best at the pitch circle position, as adjusting the center distance affects stability. Generally, packing data has high requirements for the synchronous rolling pressure between the plate cylinder and the blanket cylinder, which directly relates to image slippage and plate wear. The requirements for synchronous rolling pressure between the blanket cylinder and the impression cylinder are relatively lower. Therefore, the center distance adjustment method is often used for adjusting the pressure between the blanket cylinder and the impression cylinder. Let's take a look. Modern printing press consoles are equipped with corresponding pressure adjustment mechanisms. The above figure is a gradient diagram of pressure adjustment for a certain printing equipment, allowing digital adjustment, which is relatively easy. The above shows the adjustment of printing pressure for different color units. The following images are also interface diagrams for adjusting printing pressure on the console, which you can examine carefully. Finally, we determine the reasonable printing pressure to achieve higher quality printing. If the printing pressure is too low, the ink color of the printed matter will appear pale, causing incomplete images and text. If the printing pressure is too high, the dots on the printed matter will expand significantly, even causing an ink filling phenomenon. If the printing pressure is unstable, ink streaks may appear on the printed matter. Excessive or unstable printing pressure will accelerate plate wear and reduce the plate's durability. Excessive pressure can also deteriorate the operation of the printing press and shorten the equipment's lifespan. Therefore, we must ensure reasonable printing pressure. Looking at the image on the right, the left half shows correct printing pressure, with good dot reproducibility and high image quality. The right half clearly has excessive printing pressure, leading to severe dot expansion and overly dark colors. Therefore, we must select appropriate printing pressure and maintain its stability, which is crucial for printing. Generally, the plate pressure should be controlled between 0.1 to 0.15 millimeters, and the impression pressure between 0.1 to 0.3 millimeters. Of course, this also depends on the paper's characteristics and thickness. For BB-type printing presses, double-sided presses, the pressure is controlled between 0.2 to 0.3 millimeters. also depending on the paper's thickness and characteristics. Let's look at the print quality issues caused by improper printing pressure. This is a printed sample with excessive printing pressure. It is evident that the sample has a very dark color and severe loss of detail in the shadow areas, resulting in unsatisfactory print quality. This other image has relatively light colors and small dots, also indicating low print quality. Therefore, printing pressure is a critical indicator in the printing adjustment process. During printing, we must ensure reasonable printing pressure to obtain high-quality printed products. The above is the main content of this lesson. Thank you all.